So I mean, I'm not going to fetch any PDB in this because there's some issue with my Chimera and the version, Chimera version that I have installed. So I have already have list of multiple PDBs over here. So I will just pick any one PDB and then take you through it. Okay. So as I said, I mean, whenever Chimera opens up, it by default displays all ligands, including water, metal ions, compound bound to it. And it also shows which residues are interacting with it. So for instance, you can see over here that this is magnesium and this is interacting with aspartate 38. Okay. So if you see this carefully over here, I mean, you have, it says ASP, that is aspartate, 38 is a residue, dot A is the chain, and this is C beta, C gamma, and it's 1.5 angstrom, that is, I think is distance. So no, this is the bond length between the two. Okay. So if you want to find distance, so the way that you do is, suppose I want to know the distance between aspartate A OD1, that is one of the OH group, okay, OH group, and this is, I mean, the C double bond O and OOH you can't distinguish. So this is, so let's take this O and this magnesium. So you can go to tools and structure analysis, distances, and then you need to select two atoms for which you want to find the distance between them. So as I said, you need to press Control and left mouse button. You can select one atom, keep your Shift and Control, select the second atom, and it'll, and I mean, you can select here, or you can also go to the window in here, distances, and can see the distances. You can also create, and it does find the same distance. So there it shows that you can, you know, see distance, but you can also do create and then press create and it will find the distance between them. Okay, but you need to keep the two atoms selected, and that's the most important thing with it. Okay, so distance says is 2 angstrom. Now, one of the thumb rules of determining any atomic contact is that, does anyone know how do you know that a particular ligand is interacting with a protein, or how do you say that two proteins are interacting? How do you find this out?
So we can check if there are any bonds forming between the ligand and the receptor or any other molecule.
No, so bond, which bond you're talking about? Covalent bond?
No, sir. Like the hydrophobic bond, the electrostatic interactions.
Okay, so there's nothing called hydrophobic bond. The only bond which you have is defined as covalent bond, or you can say hydrogen bond. But again, hydrogen bond definition, as I said, is set empirically, and you can find the hydrogen bond which is there between them. That's one way. But then again, you have to use certain criteria. And one thing which you'll find in doing protein structure analysis, one thing which keeps coming up in trying to determine interactions between ligands, trying to figure out contacts, is the Euclidean distance between atoms. Okay, that the way that you find that a ligand is interacting with a protein is that you take every single atom of the protein and then find its distance to that particular ligand atom. I mean, if the ligand is 1, then you find distance with one ligand atom. If it is to 10, then you find distance with all the 10 ligand atoms. And so this is the atomic contact criteria. In order to find the one particular ligand or protein interacting, atomic contact criteria is used in order to determine whether they're interacting or not. Now, so you will end up in getting a distance. Once you find a distance, you need to apply an atomic contact criteria cutoff. So for example, one of the very typical value which is used now to determine the atomic contact, whether the two atoms are in contact or not, is a distance of 4.5 angstrom. That means if I take two atoms, okay, and the distance between these two atoms is less than 4.5 angstrom, I call this two atom to be in atomic contact. Okay, so the way that this value has come up about is that you have looked at the van der Waals radii, you add 1 angstrom to the the sum of van der Waals radii, and then say if the two atoms are within 1 angstrom away from the van der Waals radii, that means the two atoms are interacting. So 4.5 is as a kind of ballpoint figure, which comes from all kinds of atoms that you're looking at, and then you use one single cutoff rather than trying to do for every single atom. So if you're doing carbon, oxygen, then to look at the van der Waals radii, instead of doing that, you use a one single cutoff 4.5 angstrom. Okay, so that's how you know whether any two atoms are interacting or not. So for example, whatever the contact that you're seeing over here is determined based onto it. So whether this atom is involved in interaction with this particular ligand is using this very particular information. The distance is less than 4.5 angstrom. Fine. So so all that you see, I mean, this tyrosine is interacting with this particular. I think this is some unknown compound. What this is, red is water. This is, I don't know what it is. It's some unknown thing. So so you find the distance between them and then see whether distance is less than 4.5 or not. Let's look at the distance between them. So I'll click this and OH of this, and let's look at the distance, structure analysis, distances. Great. So this is around barely 4.5, 4.58 angstrom. So this is the distance between, and so based on to the 4.5 angstrom cutoff, we'll say, well, this is not interacting. So cutoffs are very harsh. That means 4.588 is also not accepted as an interacting atom for interacting atom for this particular ligand, the blue color ligand. Okay, so this is how you determine whether a particular ligand is interacting with a protein or whether the two proteins are interacting or not. So typical criteria, I will repeat it again, is to use atomic contact criteria. That means to find distance between all atoms of a protein to all atoms of the ligand. Basically, all against all distance criteria between two different components. And if you have any one single atomic contact criteria satisfying the cutoff of 4.5 angstrom, you call them to be interactive. Now, so if you have to do this, on a GUI, this is going to be a completely nightmarish exercise. So one of the ways that you can, so there is some options which are given in order to execute the same thing what I just described. So in order to activate this, you need to use something in the Chimera which is called command panel. So you go to favorites. So are all of you able to follow this, what I'm saying? Yeah, somebody is asking, this universally applicable. Yes, it's used as a ballpoint figure, and it's that's how it is applied. So all of you are you able to compute distances between atoms?
So I'm unable to do it. There's some log error showing up.
Sorry?
Some log error is showing up. So like saying that the atoms are not selected, even if I select them.
Okay. So you can, let me follow it up again. So what you need to do is you need to press Control button and left mouse at the same time in order to select it. Okay, so I'll do it again. Other thing that you can do is select and then clear selections if something is already selected. And you can zoom in and zoom out to your convenience to see that. So another problem which happens in a GUI when you're dealing with is that you think a certain atom that you're clicking is what you're selecting. But since it's a three-dimensional object, I mean, you have things which are lying back of it. So maybe you are clicking an incorrect atom at the back and it's not really getting selected. So you have to pay attention to these things, I mean, minor details. So best is to zoom out and then see that atom is lying very close to your cursor, and then you can select it. So this is a very common issue. So again, I'm doing this. So I'll press Control button and my left mouse button. I click the atom of my interest, and that's how I make a selection. And with Control and Shift both pressed on, you select the second atom, or third, fourth, whatever you want to do. So that's how we, I think you would have done torsion angle. That's how you find torsion angle for it. Any issues? So I can continue with the next section.
Right, sir. Thank you.
Okay. Okay, so what I will do is I think I did mention about pivot also. So suppose you want to keep certain atom in focus and do not want to lose the atom, because it's anyway when you move, either you rotate around, your atom will move out of the focus from your central button. So suppose I want to keep any one atom. Suppose I want to keep this particular magnesium at my center of my focus, and do not move this out of my screen whenever I try to rotate the structure. What you can do is use again control and left mouse, select it. Once you select it, go to actions and say set pivot. And once you do this, you can do whatever. Anytime you rotate the structure, this particular point is kind of pivoted to your screen. It will not go away. So that's another way to kind of make sure that the atom that you're dealing with, for which you want to find distances or whatever it is, it's set in one place. Otherwise, you rotate structure and the atom goes out of focus. Okay. So let me focus again. So this is how you do this. So let me. I need to get rid of it.
Sir,
Yeah.
so once we do any operation on Chimera, how do we undo it? Like, so for instance, we set the pivot, now we have to remove it. So how do we approach that?
This is, it used to be with the change with the, you change the view and it goes away. I'm just trying to see that this, sometime it goes away. Just a minute, I'll tell you. You can get it away from various other ways, but I'm just trying to see in the option whether you can.
So there is one option of clear selection in select option,
but
but
clear selection would only get you of the clear selection. That's what it does.
yes, sir, yeah.
So but it keeps the pivot on, and if you've done focus, it will keep the focus on. There is a review or reset is there I use VMD a lot, so that's where it is.
What if we select?
Yeah.
What
If
if
you
we
select some
select?
other atom, that will not. There are other ways to do this. I'm trying to see if there is something very simple that I can reset it. This is. No, this will not tell me the. You can change the options in the sense that you use some other. You can, for example, if you do preset or something, it will reset it. That's not how you want to do this. Let me see. Just give me a minute. It should be in the actions button actually.
So if you clear selection and click focus again, like the other things come.
Then come back. Yeah, okay. Fine.
Yes, sir.
Yeah, great. Thanks for that. Because every single program has its own quirks. Okay. Yeah, thanks for it. So I think it's correct. Clear selection, then set the focus in. So it keeps the protein the same focus. Okay. That's good. Okay, so the point which I wanted to show with this, so the distance is fine. Now what you can do is you can use command line option, and that's become very powerful. So what you do is go to favorites, go to command line, And with the command line option, there are various things that you can do. For example, you can set the background. So for example, you do not like the background, so you can set the background by a command called background. Okay, so background, let's say, and you want to have one uniform color, so you can say background solid and let's say white. It will set the background to be white. You can set some other color you want. You want to have some gradient color, you can use background gradient, and with the gradient you need to supply at least 2 colors. So it will make the between the mixture between the 2 colors in from top to bottom, so of the screen. So red to green. So this is how it looks in the background. So this is simple thing. So let me get to the solid white. Because I mean, typically when you're going to, one of the reasons you do not use black background, it's good for viewing, but for any kind of application of structures, black would eat up a lot of color, simply to set the black background. Till you have a very good reason to use a black background, nobody uses a black background. So that's kind of norm used. So another thing that you can do is, instead of trying to select, a residue by clicking it, another way to do is by using a command called select, and there is a certain format that you write it in. So you do select and then use colon. Now before colon there is, so you see this just below your command, you have, are you able to see my screen by any chance?
Yes, sir.
Yes.
I somehow feel that I'm not, yeah, okay. I thought you're not able to see. So just below the command line, you have this active models. So if you load multiple structures, I mean, I'll do it after some time. So you will see that each structure gets loaded as model 0, 1, 2, 3, and so on and so forth. So if you want to select a particular model, then you write this, hash 0 or 1 model or 2 model or whatever it is. If you do not care about it, then you simply write colon, and this is the syntax which you need to use. And then after this, suppose you want to select the all residue, then you need to know the chain. So for example, in this case, the chain is A, and then you see this dot. So if you go to any residue, you see the way it's written. So it's written as residue name 25.A, right? So what that means, I need to have a residue number first, followed by dot. If I do not write anything before dot, that means all residues. If I do this, you'll see that whole protein is selected, right? Everything is selected, every single atom, even the ligand atoms are selected. Suppose I want to select 205A. So what I can do is I can write 205.A, and it will select only this particular residue. Okay, so you can do 1 or 2. So I can do 205A, and then I can do 206A, and whether it's there, it's not there. Okay, so that's how you can select multiple residues in this. If you want to suppose select all aspartates or all lysine or leucine, you can say select lysine, and it'll just the residue name. So if you see this, it says residue name and followed by the residue ID dot A. That means if I do not have to write anything, then it will select all lysine. So every single lysine is highlighted over here. So you can then do atom bond and then show them as full Licory representation. This is known as Licory representation, what you see without any ball and stick model. So this is a representation which you can see where all my lysines are, and then you want to study them or whatever you want to do with it. So that's one way to select residue. So another thing that suppose you want to find all. So let's pick up any one ligand. Let's see. Okay, this is one single ligand. So this is GDP 201, right? So I want to find all residue within all atoms which are within 4.5 angstrom of GDP 201. So I do select, and then I do this. This is 201A, 201.A, and I do Z less than 4.5. Okay. So look at the syntax. So what you're doing is you, after colon, that means the residue you want to select. That's the residue ID 201, chain A. And Z is basically finding all residue, which are all atoms which are within a residue, or the atoms of residues which are within 4.5 angstrom. Okay? So that means all these residue that you see, are all you see selected in green, are residues which are within 4.5 angstrom of this GDP 201. So what you can do is, let me suppose I want to show only these interacting residue and rest hide everything else. So I can do is select, go to inverted selected models, which will select everything else except the part which was selected before. And then I'll do action and ribbon height, and I also hide the all atoms. Okay. So now what I have is only the residue which are interacting with my ligand 201. So I can execute it again, this particular command, and I can now show atom unshow. So everything is all side chain atoms are now revealed, and you can see what all residue which are interacting with it. Okay. So it's not all the time that you have a side chain which will interact with a particular atom. You can also have the backbone interacting with a ligand atom. So this is, so even though this seems to be a little bit far, maybe the backbone is involved in interaction with this particular residue. So that's how you find ligands, residues which are interacting with the ligand. You can also change this number 4.5. You can make it, let's say, 6, and it'll, and of course, I have hidden everything else. So let me do some more. So now, if I do 6, look at it. You pick up residues which are very, very far away. One thing that you should know and also realize it, when you're finding Euclidean distances between two atoms in the ligand and a protein, you're not actually necessarily looking at whether it crosses anything, right? So I can have distance between two atoms 4.5 angstrom, and I can have an atom which is lying between these two atoms. So that's something that that's the reason you do not use very large cutoff, because then you can have actually atoms sitting between the two atoms, and it may not be actually interacting. It may be interacting through an atom. So that's happened a lot with the water molecule, in fact. So many times you'll find that that the ligand is not interacting with any residue in the protein, but it's interacting with the water molecule. So it interacts with the water, and the water interacts with the protein. So it's called water-mediated interactions. So that also is present in protein ligand interactions. So this is something very basic that you can do in this usage of Chimera. Okay, so this is how do you protein ligand interactions. Let me see if there is something else. You can find hydrogen bonds. So you can keep the parameter as you can. You can look at it as intra or intermolecular interactions, and then apply. So it will for whatever selected atoms, it will find all interactions. So if you do intra, that means it will only find within the protein. Inter means protein and ligand, and a protein and protein, and so on and so forth. So you can say apply, it will show up. Right. So all the black color that you see is the hydrogen bond between water, and in this case water, and this is lysine 147, and then this is aspartate 190, and then so this is how you can see whether my ligand is interacting with which which atom, which residue in the protein with the hydrogen bond interaction. So for example, let's see, phosphate have lots of interaction. So you see this magnesium, right? So magnesium is making a water cluster around it, and this is coordinated with the GTP, right? So GDP, this is phosphate, right? So phosphate, the beta phosphate and the gamma phosphate both coordinate one particular magnesium. So you see, this is nice cluster of water and phosphate along with this residue. This is aspartate, and this should be okay. This is serine, and this is threonine. So this is a coordination of your beta phosphate with magnesium, and that's how they're interacting, right? So that's how you find hydrogen bond interaction. Is it clear? These things, very, very simple analysis. Okay, so what I have So I have posted an assignment, so which you can start in this particular class and continue. I'll add one or two more questions after I finish something that I want to cover. So the first is you can go to this. Are you able to see the assignment?
Yes, sir.
Okay. So I've listed two servers, what if server and a stride server. So what if server is a compilation of many analyses that you can do, very, very simple structure analysis. So let me go to this. Okay. So in what if server, so the link that I have provided to you, you can, you can go through various options which are there on the left-hand side, and then something that you understand, you can try it out. For example, you can try a peptide flip. So you upload a structure and then mark the residue for which you want to flip a peptide. So it will make cis to trans, trans to cis, and see what effect does it make. Okay. So this is something that you can go over it. I mean, not everything that you would require, but just go over all these various options. There is something which is there in the 2D graphics. It's called connected Ramachandran plot. Now, what is a connected Ramachandran plot? Connected Ramachandran plot is a plot where you, instead of plotting just the phi psi angle of a protein on a Ramachandran map, you basically connect the every single residue with, you connect the residue in the order which they occur in terms of their phi psi angle. So suppose I'm in a helix. So I'll basically have, I'll make dot in the helix region, and then suppose second residue is also in helix, third residue also in helix. My fourth residue goes into beta strand, so it will go to the beta strand, make a line between them. Basically, the residue are connected in the order in which they occur in the protein sequence. So that's what the connected Ramachandran plot. What connected Ramachandran plot is used for? Connected Ramachandran plot is used for analysis of turns. So you can see what kind of pattern of turns which occur in Ramachandran map. And if you are finding new patterns in a Ramachandran map of particular phi psi angle, you can also try to use the connected Ramachandran map to study this. So that's one of the use of it. You can also try exploring hydrogen bonds, which is, find all potential hydrogen bonds using the criteria which you want. I think they have, so every program, if you use, there is a little bit of variation in what is defined as a hydrogen bond. And this varies because, typically you do not have hydrogens placed onto it. So many programs, for example, DSSP, also first place a hydrogen, okay, and then basically start finding all the hydrogen bonds. So how do you place hydrogen itself is a problem, and so they use certain procedure in order to place hydrogens. So you can try atomic contacts. I think they probably do. So you can try, in this case, it's find atomic contacts for, I think, water. And then, so it basically, you can go over it and it says what is the cutoff that they're using in order to define contacts. But this is kind of a trove of, very basic analysis that you can try to do with protein structures. You can look at salt bridges and so on and so forth. So I'm not going over each one of the options, but I leave it to you to explore this set of options which are there. So even if you're trying to, you are trying to look at a model, you want to understand how well this, whether I have all phi psi angles in place and so, you can use what if server in order to do this. So another thing I completely forgot. So stride on the stride page, you can upload a structure and generate the phi psi angle map. So let me see if I can open one of the PDBs and show you the output. PDB, and let's pick up any PDB structure. So you can run stride and produce plain text. So I'm telling you about stride because I want you to use stride to find the conformational variations in the protein, and that's how the output looks like. So you have residue secondary structure assignments, and the important part comes over here. So when you're looking at it, the ASG part, where it says the residue structure, the secondary structure that it has, and what phi psi angle does it have, and it also tells you the area. We'll worry about this area in a later class. but it also computes the surface area of the residue. We'll see what the surface area is. So it computes phi-psi angle. It also gives you the secondary structure for it. So this phi-psi angle is what I'm kind of interested in trying for you to extract it. So just look at this particular output. So the way it is go to Stride, upload a structure, run Stride and produce plain text. And if you want to do visual, you can also do visual, which will show you the secondary structure of this particular PDB file. So this is one thing. This another thing I wanted to show. So what I'll do is I'll close this structure now. So I'm in the Chimera section again, and what I want you to show this is how to build structure by specifying the phi-psi angle. You can pretty much build the model that you want to do. Okay, so this is one of the exercises that I have given in the assignment, and the way that you do this is the following. So you go to Tools, go to Structure Editing, go to Build Structure, and in the Build Structure, you basically create a peptide. So for example, I want to create a peptide of, let's say, glycine and glycine. So let's say I write 5, 6 or whatever number of gases that I want, and I do apply. All of you able to follow this up? Because this is one of the exercises that I've asked you to do.
Can you go over it again, once again?
So you go to Tools, Structure Editing, and then there are multiple options. You have to go to Build Structure. Okay. Once you go to the Build Structure option, then you create a peptide. You do not create smiles, pups, nothing. You go to create peptide. You can do, you can add various things, but let's not worry about it. You need to create a peptide, and I've given glycine. You can give alanine, you can give leucine, whatever you feel like, and put the atoms in a new model, and don't change any other option. Okay, and click Apply. Once you click Apply, you will see a window which opens up here, which shows the phi-psi angle that I have. So you can choose the phi-psi angle. So if you see this, it says minus 57, minus 47. That means if I use this, I'll end up in generating a right-handed alpha helix. Okay, and you can, if you want, you can change this by default. You can say, I want to do anti-parallel beta strand. I can generate anti-parallel beta strand. I can generate 310 helix. I can generate pi helix. In seeding, you can change above phi-psi angle. Now, how do you change this phi-psi angle? I mean, if you change this, nothing changes, right? I mean, it only shows what is the ideal phi-psi angle in this particular row, selected rows to this and this. So the way this is done is that you basically select all rows over here, and then use this set option. And if you click set, it will change all phi-psi angles to whatever it is. So suppose I want to have, in the middle, I want to use some weird phi-psi angle. I want to do, maybe 49, 40, and 32. I mean, some phi-psi angle I pick up. Okay, I set it. So whatever phi-psi angle you want to change it over in the phi-psi box and click set, and this particular thing would change. So so remember this. I mean, if you change over here, it only shows the phi-psi angle over here. It doesn't change anything over here. So if you want to change it, click and then set, and it'll change this phi-psi angle. After this, you click apply and do it once. Okay, if you do it again, it basically generates the whole structure again. So this is, I have generated a phi-psi angle. This is generated a second structure. Let me select chain A. So these are the two different models. You can see this active model 0 and 1. I can select 0 first model, go to actions, and there is atom bonds, go to delete. So that I'm dealing only with one particular. So you see this. So this is supposed to be a 310 helix, but then there was something which was changed in the middle, and you can generate, maybe you can represent in ribbon. Let's see how does it look like. Okay, it looks completely weird, right? So because I mean the some part was 310 helix and something I had changed in between. Let me delete it again. I'll generate it again. So I'm doing this thing again. So I'll do file close session, and I go to tools, follow it again, tools, structure editing, build structure, whatever residue I want to make a model of, apply, select all the residues. I want to maybe make it 3-10 helix. So set 3-10 helix and apply. So now this is how the 3-10 helix look. If you look at a top view, you can see that it's so tightly packed structure. So if you generate the same thing for alpha helix, same thing for pi helix, you should be able to appreciate the selected model. Yeah. Let me show everyone. That's how the 3-10 helix looks. So tightly packed interior of for the 3-10 helix. It's kind of really twisted in this particular case. So alpha helix you can also similarly construct it and see how does it look like. And you can look at the side chain. Okay, all glycine, so there's no side chain. You should also generate structure for, let's say, for leucine and see how the side chains. I mean, how basically they go out from the kind of decorate the chain or not really interfere anywhere in the central of the helix. So this is one thing. Okay, let me show another thing in this. Okay, let me hide ribbon. And I'll do something. What I'll do is I'll change the torsion angle for one of the torsion angle and see how does it change the structure. So in order to change the torsion angle, what you need to do is go to tools, same structure editing, and adjust torsions. Okay, and for torsion, you need to define a bond, and by default it takes I-1 and I+1 of that particular bond in order to define the torsion angle. So you don't have to worry about it. So let's say this is my N, this is C alpha. Okay, so this is carbonyl, not C alpha. N, C, right? So let's look at this particular bond. So this is N, C alpha. Okay, so this is the phi angle that I want to change. So what I do is, in order to select atom, you need to point your arrow to that particular atom and then select it, right? For the bond, you need to do the same thing, but for the bond region. So you click the bond gets selected. Structure editing, basically hide somewhere in the between, adjust torsion. And you need to click this activate. Okay. And if you click activate, basically you can see it's going from N to C alpha, and then automatically you would have picked up the C on one end and the other C, the C prime on I-1 and C for the other end. And you can now use this dial in order to change the torsion angle. And you can see how does changing one torsion angle. So this is changing one torsion angle. How does it change the whole fate of that particular all fragment that is lying next to it? Okay, so you can manually set it also. Maybe I can make it -57, which is like alpha helix. That's how you can change the torsion angle. I mean, how the torsion angle can be changed, and you can see the effect of the changing of torsion. So so that's the reason it says that we pretty much define the backbone conformation simply by looking at the phi angle. If you change any one angle, you can simply change whatever is happening beyond that particular segment beyond that particular phi angle. So this is the thing I wanted to show, and I think that's pretty much. Yeah. So all of you are able to navigate the RCSB site. Is there any problem that you have navigating RCSB site? Let's close this. Any issues that you have in going through the RCSB site? It's pretty intuitive nowadays. I mean, it used to take some time to actually go over it. But let me tell you one or two features of this, and then I'll probably close. So I've chose one. Let me choose some other. So RCSB, I choose 101M, and you can do something very interesting. So in this, you can see that to which uniplot which sequence UniProt ID for which you have this structure. It says, whatever the P02185, you can click, you can go to that UniProt. So this link is, I said, is, even though this has been refined for multiple times, but you can still have lots of errors in this cross-referencing. What is interesting over here nowadays they have done is that you can find similar proteins. Please pay attention to this. You can find similar proteins by using a sequence identity cutoff or by using structure. So what I want you to do is to find sequence identity by using a sequence identity cutoff. Use 100% and then list all the structures. That means it will give you all the structures for the exact same protein. So it says there are 4 structures solved for this protein, and that's one way you can find how many structures that are known for. So if you know if you have a PDB ID of one protein, then you can find all structures which are solved for that particular protein by using this particular option. If you decrease the sequence ID, let's say I use 90%, then you are finding structure of homologous proteins, as well as for protein when there are significant mutations that are present in the protein. So that's one way you can explore these things on the RCL side. That's all I want to cover for this section. So what I will do is I will pause for another half an hour and I'll let you do the exercise. I will start it. I am here. I'm not going to go. You can ask me questions, but you start doing your exercises because I want you to go hands-on, and then if you face any problem, you should be able to mention this to me and we can address it. In this particular session. After another half an hour or so, I want to discuss about something which is known as protein structure alignment. So I'll talk to you about around 15 to 20 minutes about how this is done, and then I'll show you on the Chimera how to do this, structure alignment. So any query that you have with this? Okay, someone will ask question. Okay, so